All right, so before we start this last example, we want to have this picture of the mean value theorem in our mind. What does the mean value theorem tell us? It tells us that if we have a function that meets certain criteria that have to do with continuity and differentiability, then somewhere on that interval of continuity and differentiability, there's a value, an input value, an x value in between the endpoints of that interval, at which the derivative of the function is equal to the average rate of change of the function over that same interval. So we want to sort of keep that picture of the mean value theorem in our mind so that we can notice numbers and letters that show up in this problem, and we can make a connection and see how that mean value theorem can help us. So before we start this problem, I hope you will help me correct a very grave error. That last line says for 0 is less than t, which is less than 60, must there be a time t for which that should be t, for which a of t equals 0. So if you could please make that correction. Okay, so here's what we have. We have a car that's going along a track. We know that the only information we have happens between time 0 and time 60. We know some values of the car's velocity, and we know some values of the car's acceleration on that time interval 0 seconds to 60 seconds. We know both acceleration and velocity are continuous. We know the acceleration exists, so that means the velocity must be differentiable because its derivative exists. And the table above shows selected values. So the question they're asking for time on the interval time 0 to 60, must there be a time t at which the acceleration of the car equals 0? And justify your answer. So what we want to do, we probably sit down and take the AP test, and we see this problem, and we're like, oh, you kind of just go through the year in chronological order. So one good tactic would be to look here at the acceleration values. We learned the intermediate value theorem. If I could find an acceleration that is bigger than 0, so positive, an acceleration that is less than 0, negative, then I could use the intermediate value theorem, which is kind of a lot easier than the mean value theorem, has fewer parts. And I could just use the intermediate value theorem by looking at the a values. So now I do that. I scan through the a's, and I see plenty of positive acceleration values, but I see no negative acceleration values. Does that mean that the acceleration is never negative? No, it just means that of the data I have, I don't have any negative acceleration values to choose from. So I hope you had that experience of thinking, oh, I wonder if I could use the intermediate value theorem. So you try it out, but there are no negative accelerations. So no negative acceleration values. So you have to have this thought process. Oh shoot, I can't use the intermediate value theorem because I found no negative acceleration values in this table. So luckily we have another trick up our sleeve, and that's the mean value theorem. So can the mean value theorem help us here? Turns out it can, but we have to be able to make lots of connections, and especially notice that we have numbers and letters here that don't match up with that original definition that we learned. We're used to, when we see a mean value theorem problem, having somebody ask us, isn't there a value x for which f prime of x equals, and we don't have a derivative notation in this question. So number one thing, doesn't have to be the first thing, but one thing we're going to have to notice is that a of t, which we're asked to prove the existence of a value of, can be written as a derivative. What derivative is a? That's the same as v prime of t. And we want to know if there's some t for which v prime of t equals 0. So that's the number one connection. Know that you can't use the mean value theorem to help you unless you've recognized somewhere that you have a derivative. So we've been asked to prove the existence of this acceleration value. Acceleration is the derivative of velocity. So here's my new question that I'm thinking in my head. Is there some time t for which v prime of t equals 0? So that means that I want to be applying the mean value theorem to the v function. Because remember, f is a function that's differentiable and continuous, then for some value c, f prime of c. So that would be us applying the mean value theorem to the f function. Here we're going to apply the mean value theorem to the v function to prove the existence of some specific value of v prime. So another thing that we're going to have to figure out, what are our a and b here? So you can see this notation here might lead you to believe that a and b are 0 and 60. So that's going to be a good thing to check out. That's maybe half of the time, maybe more than half of the time on the AP test when you have a mean value theorem question, these numbers here on the end of this continued inequality are going to be your A and B. So now we're going to have to check them. So what's that going to mean? We're going to need to have V of 60 minus V of 0 over 60 minus 0, that's f of b minus f of a over b minus a, except we don't have f's, we have v's. We want that to equal this very special output value of 0. So is this true? What's v of 60? 10 minus v of 0 is negative 20. And this would be 60 minus 0. Well, shoot, because that makes 30 over 60, which is 1/2. I need to choose my A and B so that I end up with a true statement here. This was not true. I need to pick a different A and B so that when I find the difference quotient, the average rate of change, I actually do get 0. So you didn't waste any time. If you always want to check these two numbers here, a lot of the time they're going to work. Maybe you could have checked them in your mind without writing them down like I did. It's totally up to you. But we're going to have to find A and B, and it's not 0 and 60. So this takes a little bit of thinking, but you'll find this is like the second most common case, is that it wasn't that it was the two endpoints I was given, but I do want my difference quotient, my average rate of change, to equal 0. Wonder what circumstance is a fraction going to equal 0? When the numerator is 0. And what's in the numerator? It's v of b minus v of a. And that difference is going to equal 0 whenever v of b and v of a are equal. So we're going to look through my list of v values. I'm looking for any two v values that match. Turns out there's only one option here that I see. You might find in a different problem that there's more than one set of v values you could choose. But here, I now conclude that I'm going to have my A equal 0 and my B equal 25. Notice this top line here is the inputs. In this case, the T's. And A and B are inputs. So I'm going to choose A is 0 and B is 25. So that I can have a difference quotient, an average rate of change that is equal to 0. So I'm going to erase what's here and start over. All right, I said I'm going to let my A equal 0 and my B equal 25. So here's my new average rate of change. Remember, my work to use the mean value theorem problem to justify the existence of some t value takes two parts. I have to show that I found an average rate of change that equals the number I was supposed to find. And then I have to give a write-up stating that I checked the hypotheses of the theorem and that I can therefore make my conclusion. All right, so this is the part where I find the average rate of change. The acceleration at time t is the same as the derivative of velocity at time t, and we want that to equal v of 25. You could do this in fewer steps, I suppose, minus v of 0 over 25 minus 0. Well, v of 25 is negative 20 minus negative 20 all over 25 minus 0. And I have plus plus here. And that does, in fact, equal 0. So did I show that there were two values, A and B, in this case 0 and 25, for which the difference quotient is equal to 0? Yes, I did. Now I'm going to use the typing feature to type up how I would write up the rest of my conclusion. All right, so this is what I wrote as my write-up here. Since v of t is continuous on 0 to 25, with the endpoints included, and differentiable on 0 to 25, open interval, the mean value theorem guarantees, that should be a lowercase g in guarantees that there is at least one time t in between a and b are 0 and 25, so 0 is less than t less than 25, for which v prime of t, that's the part the mean value theorem tells us, equals a of t, that's the part that we know, that v prime equals a, must equal 0. The 0 comes from, whoops, this part here where I already performed this calculation. Okay, so a couple things to notice. Some people get nervous giving this answer because they notice that the problem asked for the interval 0 to 60, and we've said that our answer is on the interval 0 to 25. Well, you have to use an A and B in your answer that actually gave the difference quotient, that actually gave the average rate of change that you were supposed to find. Now, if we promise that we found an answer on the interval 0 to 25, must our answer be on the interval 0 to 60? It must. So the fact that our interval is smaller, that's okay. But our interval has to have use an A and a B that matched our average rate of change. And it has to be the same interval that they used or an interval that's smaller. Other things, yeah, so just to notice here, this is us applying the mean value theorem to the function v. And the mean value theorem tells us that if that function, in this case v, is continuous and differentiable and blah, 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 then it tells us something about the existence of a special value of v prime. The original problem asked us a question about a. So we have to make that connection. We have to use the mean value theorem correctly, which is to look at characteristics of v and use that to prove the existence of v prime. But then we also have to let the reader know that we understand, because we studied chapter 3, that v prime is the same as a of t. So make sure you have this v of t and v prime of t. These guys have to match. But then you have to also tell us that you recognize that finding a special value of v prime is like finding a special value of a. To make that connection back to the original problem, you were asked to prove the existence of this special value of a. Cool, so come to class with all the questions you have, and we'll do lots of practice on the mean value theorem.